One of the challenges with AI is the lack of explainability. So you have models that seem to output really accurate predictions and diagnose things that are unseen to the physician. We don't really know how these models are doing that. And I guess this next session between myself and Manolis will explore some of the important concepts around the explainability of AI models. There was an editorial about AICG that referred to AI models as being a little bit like magic, and their message was maybe we should just trust what it's doing and then get on with it and accept the predictions. I think a lot of clinicians need a bit more than just trusting magic. They need to see what the model's doing. And I think it's often important to look under the hood, as we say, to work out what is going on. This is an example, and there are lots of such examples out there in the literature. They trained a model to look at a picture and say whether it was a wolf or a husky. And it turns out the model wasn't really looking at the animal. It was looking at the background, and it was looking at whether there was a snow in the background. If it was snow, it called it a wolf. And if it's no snow, it called it a husky. So it's important to understand how the things work, because by uncovering these things, you realize the model's not doing exactly what you want it to do. And that's important for us clinicians. So AI models are great. They are very accurate, but they are inherently black boxes. They are data-driven approaches. You put a lot of data in, the model works through the image or the signal and outputs a prediction. But what goes on in the middle is unseen and very difficult to disentangle. But it's often said that we do need some explainable AI, partly to improve what we're doing, to justify, control, and discover what's going on in the models. So how are we currently explaining AICG outputs? There are several ways of doing this. There are several post-hoc techniques that look at which bits of the signal are most important for the model in making its decision. So here's an example here, and I'll walk you through a couple of our works to show how we've done a bit of explainability analysis. So a couple of years ago, before we started some of the stuff I showed you yesterday about predicting future outcomes, our first study was actually a very simple task important to electrophysiologists. We wanted to take an ECG and work out whether the mechanism was atrial flutter or was it some form of other atrial tachycardia, because for me, it's helpful to plan my procedure and how to ablate, whether I need to go left or right side in terms of the procedure. So we trained a model to look at ECGs and then predict whether or not it was typical atrial flutter, cavo tricuspid isthmus dependent flutter, or was it some other mechanism where you'd have to ablate somewhere else rather than the CTI line. Without going into the results in too much detail, it turns out that we could do it quite accurately. If you look at the confusion matrix, it tends to get it right around 80% of the time or more. So by looking at the ECG, the model can understand whether the mechanism is CTI dependent or not. What we tried to do was try to work out what the model is doing. And with this, you can do something called saliency mapping. So it's a post hoc technique. It's not really true explainability. But what you can do and say is, where's the model most interested in when it's trying to make its predictions? And then you, in a post hoc way, say, phew, it is doing what I think it's doing. So in this scenario, we were at least relieved to see that it's looking more at the P waves or the flutter waves rather than the QRS. You'd be slightly concerned if it was looking at the QRS to work out whether it's atrial flutter or atrial tachycardia. So the fact that it's looking at the P waves or the flutter waves gives us some reassurance that the model is doing something as we wanted to do. So you can do something called saliency mapping after you've had the outputs to look at which bit of the signals are most important for the model in making its predictions. I'll give you another example. We had a model that could output a predicted survival curve for each individual, so we can tell when someone might die based on the ECG, and it sort of guesses your rough time of death. And here are two examples where individuals died and the predicted time of death was close to the actual time of death, and two examples where the curves were fairly flat, and these are individuals who did not die. And what we're using in this model is to track patient's health over 10, 15 years. So each single dot is an ECG, and we can make predictions about how long the person has to live based on the ECG. And you can see the predictions drop down over time, and at the time of death in the red lines, it matches the patient's time of death. What we found out was the predictions correlated quite well with long-term mortality. So if you're in the highest risk quartile based on the prediction of ECG, you had the worst outcomes over 20 years. So we had this model that was quite accurate in predicting time to mortality, but we want to understand what it was looking at. And again, we want to do some explainability analysis, because if you say to a physician, I have a model that can predict your date of death, they'll go, well, what is it looking at? Why is it doing what it's doing? So again, we did some more post-hoc analysis. In this case, we employed something called a variational autoencoder. So it's a bit different from the saliency mapping, which just looks at bits of the ECG most interesting. Here, we're looking at what types of morphologies are most important in making these predictions. And to do this, we developed something called a variational autoencoder, which essentially is a deep learning architecture that takes a signal on one end, puts it through this architecture, and spits out the same signal at the other end. But in the middle, it reduces dimensionality down to a small number of features that can capture the ECG and the essence of the ECG. And with that, we can try and understand what these models are doing. So we managed to essentially represent the ECG entirely with around 20 different features. You can see the different features. One encodes maybe more of the T wave. One looks at more of the QRS morphology. One is the PR interval. One looks at the ST segment and the QT interval. And these features combined describe the entire ECG. So you can start to now understand which of these features are most important in your prediction. So what we did was to take our mortality prediction model and say which of these features are most important, and we can then look at the morphologies. In this case, we found that the red signals are the most high risk and the blue signals are the most low risk. We found that the broad QRS is bad, the abnormal T waves are bad, the abnormal ST segments are bad. So this again fits in with our understanding of high-risk ECGs and gives some post-hoc confidence about what the model is doing. Again, I'll just play the video of how we're now trying to implement that in our interface. So, we have an AI ECG platform where you can put in an ECG, it outputs predictions, so it's running the model, then it outputs sort of high or low risk for a range of cardiac conditions and sort of risk of events in the next 5 years. But I think what's important to physicians is not just seeing these outputs, but being able to have a look at the ECG, do some saliency mapping, have a look at which bits of the ECG is the model is looking at. So again, gives the physician a bit more insight into the black box model rather than just spitting out outputs and having physicians trying to accept what is being provided. You can do explainability analysis not looking at the signals. You can look at associations of the outputs. You can understand what is the biology behind the predictions beyond just the signal. So we've done some work looking at whether the high-risk predictions are associated with things we understand, like adverse features in MRI, whether it's associated with adverse or specific genotypes that are associated with adverse outcomes. So you can do explainability analysis in various ways, not just on the signal, but also doing associations with other phenotypes and genotypes. Having said that, all of these things are post hoc, so they are what I call a fudge. They don't really look at explainability because you've done the model and then after you work out what it's trying to do. There's now a push towards trying to get more explainable AI models, and we're developing something called a VAE scan model that I wouldn't go into too much detail, but essentially it takes both the morphology and the prediction together in the architecture. So it links the shape of the ECG and the prediction. So you can then begin to look at, on an individual basis, what is the exact signal it's looking at to make the prediction. So in this case, it's telling you why it's saying someone's old, why someone is calling someone male or female based on specific morphologies of the ECG. Just to finish off with this slide, but this all comes down to this. When we have AI ECG models that are very accurate, people say, I want you to tell me what it's doing. But this performance explainability trade-off occurs throughout AI models. It comes down to what we value most as clinicians. AI models that are most accurate are, by definition, not explainable, and the explainable models perform less well. So here are 4 or 5 different models, and as you go along the x-axis, the model is more explainable, but as you can see, the performance drops. So we've developed 5 different models to do the same task, but the more explainable it is, the worse the performance. And if you're a physician, would you want a model that's more explainable but performs less well, or vice versa? And if you were the patient for which you are having your data used to make a prediction, would you want a model that is more accurate or more explainable? And that's a question that is still very much open in the world of AI. So we might have to end up trusting magic after all. Thank you very much.